Welcome again to Year 10 Physics. In this video we're going to look at energy questions, so leading on from the motion questions in the other video. It's best if you watch the motion video first because at the end of this one there's combination questions that involve motion and energy. So starting off with our equations, looking at the variables we have down the bottom, looks like we have significantly more. We also have equations which are different from each other. In the motion, we really only had three equations. Okay, we have work equals force times distance. Now, this is the equation when distance is with a d. I know that's annoying because it's with an s basically all through motion except for this example here. Power equals work divided by time. So the amount of work in the amount of time, and power is measured in watts. So you'd be familiar that lights or fans or heaters, lots of things have a wattage attached to it. What that's talking about, pardon the pun, is the power. So the more work that can be done in less time means that power is more. If the amount of work done is over a long period of time, so the number on the bottom is large, we're going to get a small amount of power. This is energy. And the little p means potential energy. Potential energy equals mass times acceleration, which is gravity, times height. Now this type of potential energy is gravitational. This type of energy is kinetic. And the kinetic energy equation is half mv squared. So the mass and the velocity. So velocity plays a bigger part in kinetic energy, which is the energy of moving things. This is Newton's second law again. And then we have an efficiency equation. So energy efficiency equals the useful energy divided by total energy times 100%. Hopefully you've seen that one in Year 8 physics and you're pretty competent at using it. It's not particularly difficult. The most difficult bit is just working out what the useful energy is. With this video, what you need to do is you need to download the question sheet. And the link to that is in the description. You're going to get more benefit out of this video if you attempt the questions first. So if that means pausing the video as you go, or if that means attempting the whole lot first and then going straight through the video, that's up to you. But you're not going to get much benefit if all you're doing is copying down the answers as we go. That's not going to help you. So question 1, what are the units for work? Work is measured in joules. Energy is also measured in joules. How much work has been done when an object has been moved 8 kilometers with a force of 25 newtons? So what have we been given? We've been given a distance and we've also been given a force. What do we need to work out? We need to work out what the amount of work done is. And the equation you want to use is this one, work equals force times distance. This is a pretty simple calculation. So 200,000 joules, or you could put 200 kilojoules for that answer, kilo being 1,000, so if you think of kilograms. Number 2, what is the force required to do 2,500 joules of work on an object when moving it 500 meters? So what force do you need? So again, we've got work, we've got a distance, we need to work out what the force is. Using the same equation, we can rearrange this equation so force is isolated. So work divided by distance, and then it's a simple calculation. So this would happen if there was a force of 5 newtons. Next question. How much power is required to do 1,500 joules of work on an object in 18 seconds? Okay, so this one's different. We've got work, and we've got time, and we need to work out power. Power equals work divided by time. Work's 1,500 times 18. It's in seconds, it's not in minutes, so that works for us. 1,500 divided by 18, 83.3 watts. Now you have to have units for every single answer that you do. You're going to lose marks if you don't put units there. Again, because 83.3 is just a number. Could be anything. Could be kilograms, meters, kilometers, miles, degrees. You need to have units there, otherwise it has no meaning whatsoever. Question 4. What is the weight force of a 55 kilogram object? And second part, how much work needs to be done for that object to be lifted 11 meters off the ground? So there are two questions here. So all of the variables that we have up here, and these are the two things we need to find out. We need to find out the force first. Force equals mass times acceleration. Now the acceleration, in this case, is gravity. That's how you work out weight. Mass times 9.8 on Earth. So acceleration equals gravity equals 9.8. So if you weigh 55 kilograms, the force that you're applying downwards onto the surface of the Earth is 539 newtons. The work equation, force times distance. So we've got a force here. We have a distance which is 11 meters. So the work done is 5,929 and work is in joules. Question 5. We've got a hairdryer producing 500 joules of kinetic energy and 1200 joules of heat energy in 15 minutes. If it uses 2500 joules of energy from its power source, what is its efficiency and how much power does it use? This question is interesting, and it all comes down to what you define as useful energy in this case. Let's have a look at the variables we have. Now I've chucked in efficiency on this one. It's only on this question. So we have a time, we have the amount of energy, we need to find power and the efficiency as well. So I've defined efficiency as just the heat energy in this one. However, you could argue, and quite reasonably so, that the kinetic energy of the fan, in fact, that's probably a better answer. Anyway, so efficiency equals useful and total times 100. So if you put 1700 on top, I'm happy to go there. So 1700, you'd be looking at about 70%. So the second part of the question asks us how much power does it use? We need the power equation. Power equals work divided by time. The amount of work done, regardless of whether it was useful or not, is 2,500 joules. And those joules are done in 15 minutes. So the power of the hairdryer is 2.78 watts. In question 6, we want to work out how much potential energy a 68 kilogram chimpanzee has when it's sitting in a tree 12 meters above the ground. So we have the mass, we have the height, and we also know what gravity is on Earth. We need to find the energy. So which equation are you going to use? Potential energy equals mass times g times height. So we have the mass is 68, g is 9.8 on Earth, and it's at 12 meters. 7,997 joules, so 8 kilojoules is the amount. The thing with these ones is it seems like not enough joules. Because if you think of 8 kilojoules to do with the amount of energy in food, it doesn't seem quite right, but it is. A car with passengers has a mass of 800 kilograms, travelling at 105 kilometers an hour. How fast is this in meters per second? And what is the kinetic energy of the vehicle? So we've got a mass, we've got a velocity, and we need to work out the energy. So the first thing we need to do is we need to do the conversion. We need to turn this into meters per second. So divide it by 3.6, 29.17 meters per second. The second part is we need to work out the kinetic energy of the vehicle, and the equation's a bit of a given, isn't it? Energy equals half mv squared. We substitute the values in, 800, 29.17, and we get 340.3 kilojoules. So about 50 times as much potential energy as a chimpanzee just sitting there. I guess that makes sense. Question 8. What is the mass of a swimmer that is moving at 2 meters per second and has 165 joules of energy? We have energy, we have velocity, we need to work out the mass. So it's moving, so we're going to use the kinetic energy equation. And then we're going to substitute values in to work out what m equals. With the half, we multiply both sides by 2, and then we divide both sides by v squared, which gets m on its own. Then we put the numbers in and we come out with 82.5 kilograms. Question 9. A ball is held at the top of a dam wall. How high is the wall if the ball has a mass of 0.5 kilograms and 563.5 joules of potential energy? So we have the mass, we have the amount of energy, we know what gravity is, We just need to work out what the height is. Bit of a given that it's the potential energy equation. And then we isolate the height by putting m and g on the other side, dividing both sides by mg. So 115 meters, that's a mistake, that should be an h. A 75 kilogram diver, this one looks a bit longer, stands at the top of a cliff ledge 40 meters above the ocean. Now this is realistic, these guys do dive from 40 meters up, don't try it yourself. How much potential energy do they have? How much kinetic energy will they have when they hit the water? What will their velocity be when they make impact? Okay, number of things going on here. Let's work out the potential energy first. Mass times gravity times height. 75 times 1.8 times 40. So they have 29.4 kilojoules of energy. How much potential energy do they have? How much kinetic energy will they have when they hit the water? The potential energy when they hit the water is 0. So all of that energy has become kinetic. So when they hit the water, they'll have 29.4 kilojoules of energy. Kinetic energy, that is. What will their velocity be when they make impact? So we use the kinetic energy equation, half mv squared again. Substitute the energy in, leaving velocity on its own. So we times both sides by 2, divide both sides by 75, we get v squared on its own. We need to take the square root of the left-hand side to get v on its own. So 28 meters per second when they hit the water. That's pretty quick, that's why I said don't try it yourself. Castle Rock near Albany in the Parongarups. 15-ton boulder. There is a boulder up there. Everybody's probably seen it who's hiked up there. Looks like it's balancing. It's not. It's actually attached underneath. It's just weathered around to make it look like it's balancing. Eventually it will fall off though. Has 39.69 megajoules. Okay, mega, million. 39.69 million joules of energy. It's a pretty big boulder. How far above the ground does it sit? If it rolled off Castle Rock and fell, how fast would it be travelling when it was halfway to the ground? This one's a bit trickier. So let's have a look. We use the potential energy equation to work out how high above the ground it is. So 270 meters above the ground. Halfway down, half of the potential energy will be transformed into kinetic energy. So this is the total energy. Halfway down it's got half of that in potential. The other half has all been converted into kinetic. So 19 megajoules of energy. Then we use the kinetic energy equals half mv squared. And we substitute the values in. Pretty similar to the last question. This time we end up with 54.1 meters per second. Makes sense because it's a lot higher up, isn't it? When you discount or ignore air resistance, everything's pretty much going to fall at the same sort of rate. When it hits the ground, all of the potential energy is converted into kinetic energy. So when it hits the ground, it's going to have 39.69 megajoules of kinetic energy. It's going to be going a hell of a lot faster than that. So it's fallen 135 meters when it has that much velocity. Number 12. There's 5 parts to this question. It involves both motion and energy. We have a rocket. It's been launched on an oval by physics students. Pretty risky. 12 kilogram rocket. We want to know the final speed of a 12 kilo rocket that's flying vertically with an initial speed of 350 meters per second. If it has been accelerating, that's pretty rapid acceleration for 36 seconds. And how much kinetic energy does it have? So we'll start with part A. What is the final speed of a 12 kilogram rocket? Flying vertically with initial speed 350 meters a second if it's been accelerating at 41 meters a second squared. It's pretty rapid acceleration for a reasonably long period of time. How much kinetic energy does it have at this moment? So we need to find 2 things. So velocity equals initial velocity, acceleration time. We've got all of those things to work out the velocity. So it's going at 1,826 meters a second. It's pretty serious. So how much kinetic energy does it have? So we've got the mass and we have the velocity. So we know to use the kinetic energy equation because we've got the mass and the velocity. And we just substitute those values in. We come out with 2,005,000 656, 2006 kilojoules, or you could put 2.0 megajoules if you wanted to. At year 10 level, we probably, unless you're told otherwise, we'd be happy with those. The other alternative is scientific notation for a number that big. So it'd be 2.0 times 10 to the 1, 2, 3, 4, 5, 6. Part B. The rocket runs out of fuel and begins to fall to the ground. If the rocket is 2,650 meters above the ground, how much potential energy does it have? This one's not too bad. Mass times gravity times height, 12, because we know it's 12 kilos, gravity, and its height is 2650 meters. It's got 312 kilojoules, 311, 640. If you're going to use another equation, use that exact number, but if you're just answering this one, you put it as 312 kilojoules. So that's the three significant figures. How fast will it be moving vertically when it strikes the ground? Where has all that potential energy gone? Here's our potential energy. How fast will it be moving? It's all become kinetic energy. So this value is the same as this value when it strikes the ground. So there's no potential energy anymore. It's all become kinetic. The amount of energy, we've got the mass, but we don't know what the velocity is. So we need to go through this process of isolating V and then taking the square root of the rest. There should be a closed bracket there. Going at 2,279 meters per second. 2 kilometers a second. Look out. That's going to be pretty bad. I doubt this was done by physics students. If it takes 0.02 seconds to completely stop when it hits the ground at that speed, how much force does it hit the ground with? F equals ma. But we need to work out what the acceleration is, don't we? Acceleration is final velocity minus initial velocity over time. The final velocity is 0. The initial velocity was 2,279 meters per second divided by 0.02. So the acceleration is negative 113,952 meters per second squared. That's pretty serious. So again, force equals mass times acceleration. We now have an acceleration, we have a mass. That's a seriously ridiculous amount of force, 1.37 meganewtons, so 1.37 million newtons. I would say that would do a lot of damage. How much work has been done on the ground if the rocket leaves an 80 centimeter dent in the ground? I don't know if this is actually legitimate, but if you get a question like this, you've got the work equations asking for work. We've got a force, we've got a distance. The distance is 80 centimeters. So you've got a 0.08 meters. We know what that force was. So the work done on the ground is 1.09 million joules, 1.09 megajoules, which is a lot. Hopefully that was of use.